Today we are tackling a critical challenge in blast furnace operation, addressing excessive delta P process. This requires a multi-faceted approach focusing on burden quality, distribution, thermal control, and hearth management. So we are going to look into the three aspects which helps in focusing the delta P process. That is, once again, I want to repeat the burden quality distribution, thermal control, and hearth management. Our immediate concern is direct control of delta P process. Operator must constantly monitor and maintain pressure difference or delta P process below its maximum allowable value, typically 1.6 to 2 bar. If this limit is exceeded, the blast volume should be reduced immediately, as all operator is to do, and it's getting recommended in standard operating practices of each furnace control room. Also, modern furnaces even have an automatic system that reduces blast volume and delta P max is reached, preventing process upset. When you reduce blast volume, you also have the option to decrease top pressure to maintain a stable gas flow and to your velocity. However, if your primary goal is to stabilize burden descent, maintaining top pressure at its maximum is often preferred. So we have to also choose that what is the context and what is to be done. So situation will decide. Now coming to a foundational step in improving burden permeability to minimum fines, we achieve this by implementing rigorous screening of burden material before charging, aiming for less than 3% below 5 mm, and it also crucial to select material with good reduction degradation properties to limit generation of fines within the furnace itself. If fines are unavoidable, their even distribution is paramount. They should be well blended throughout the ferrous burden and distributed evenly over the furnace radius. For instance, using 7 or more chute position with a bellless top can prevent the formation of low permeability ring. Next, we focus on optimizing softening melting behavior. We should choose burden material that exhibit high softening temperature and a narrow softening melting range. So key is high softening temperature and narrow softening melting range. This is key because it ensures the cohesive zone remains permeable for longer and at a higher position in the furnace. Excellent example include super-fluxed sinter and olivine pellets. Strategic blending is also highly effective. Even combining a relatively poor quality lamp ore with a good sinter can improve the overall softening and melting behavior. The stronger components create a skeleton that support weaker material, maintaining a structural integrity and permeability. Furthermore, we can utilize permeability enhancer or a spacer like nut coke, scrap, DRI into the ferrous burden. This material remains solid at just above the cohesive zone temperature and creating crucial pathway for gas and liquid and helping to break up the cohesive material. So placing nut coke, especially in the wall area, can help lower reduction gas and heat requirement in that region. Coming to the our next slide, which is about the integrity of coke layer, is absolutely critical. We must maintain adequate coke layer that are sufficiently thick and well distributed to physically separate ferrous layer, preventing them from fusing and forming impermeable bridges. A minimum metallurgical coke layer thickness in belly of about 15 centimeter 15 centimeter, roughly 3 times the mean size of the coke size, is considered essential. uh, Essential. We also optimize both ore and coke layer coke layer, ore and coke layers not exceeding 70 to 80 centimeter at throat, and coke layer not smaller than 34 centimeter, and that we have to aid in memory that this should be the navigation parameters. Moving to the hearth, it is crucial to manage hearth liquid levels. The goal is to maintain liquid level uh, of hot metal and slag in the hearth as low as possible. Though efficient and timely casting practices are there, but we must have to focus these very precisely. The practice is vital because it reduces the upward buoyancy force on the coke bed, which in turn prevent the compression of the cohesive zone and significantly improve body and descent. To achieve this, continuous or alternate casting regimes are crucial. Now let's discuss proactive thermal control and body distribution. Operator must monitor and react to cooling trend. An increase in direct reduction and can accelerate body descent rate are early indicators of such a trend. When these signs appear, operator should react by increasing pulverized coal injection by 10-20 kg per ton hot metal. We have to increase provided the flame temperature is 21 20 200 can be maintained, or reducing blast volume uh, also is the way out. Ideally, this should be done while maintaining a constant raceway adiabatic flame temperature, as I have just said, and the oxygen input to effectively raise the cohesive zone to its optimum position. A critical part of thermal control uh, is achieving and ideal body distribution. This strategy include maintaining ore-free center, typically 15 to 20% of furnace dia, to allow gas to distribute efficiently from center to wall. This approach ensure early horizontal and facilitate horizontal layers and facilitate the strategic distribution of fines and nut coke, leading to a stabilized blast pressure and gas flow. Conversely, it's essential to avoid inverse profile where central burden surface is higher than the wall, as this has been shown to cause poor permeability and severe tipping of the tuyers. Now, our next challenge involves addressing adherence and scaffolds within the furnace. For lower scaffolds, which are the resolidified slag in the wash belly area, implement cleaning actions such as charging coke blanks and decreasing slag basicity by 20%. This helps to facilitate their melting and removal to prevent upper scaffold in the upper stack. It's crucial to monitor alkali and zinc loading, minimizes fines input, and conduct cleaning operations. These operations can include lowering the body level to even 14-15 meter above the tuer using water spray to control top temperature to dislodge them, and such type of action also have to be taken in order to take care of the anomalous situation. Now coming to the controlling moisture inputs, image of raw material, water droplet or moisture gases, then a these all these controlling moisture inputs by the gases are important, because controlling moisture, unless until we control moisture, it's vital to minimize the raw material reduction and maintaining the uptake temperature. So in order to prevent water leakage within the furnace, this high moisture analysis is to be gauged by approving equipment which is rightly calibrated. So we can say that high moisture input also lower the isotherm and shorten the effective process height, leading to less efficient gas reduction and an increase in direct reduction. And once direct reduction increases, the consumption of coke also increases, leads to higher coke rate in a big way, and there is a reduction in production and productivity. To counterattack these, utilizing moisture gases to compensate that, we have already mentioned that its calibrations and its monitoring is to be done in a regular interval of time. because many times if it gives a wrong signal, uncalibrated guesses, then we may deceive by the values that is getting displayed on the gauges, and we may not have a precautionary corrections, or our precautionary correction may be delayed, which for which we may have to put on a lot of penalty in terms of coke rate, abnormal furnace behavior, hang and slip situation, and so many things. So by diligently applying this multifaceted strategy, we can effectively manage and mitigate excessive delta P process, ensuring a stable and efficient blast